Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Well, it's great to be back here. I was saying to Steve Seitz that I wanted to meet all of the new faculty that have been hired since I was here full time, and he said, well, come back and be in our Distinguished Lecture Series and you can meet everyone. And it's been great so far today. I see why all of you new faculty who I met were hired, because you would have passed my interview with flying colors too. It was just a really fun day so far, and I'm looking forward to more tomorrow. So what I thought I'd do today is give you kind of two talks in one. The first talk will be longer, the first 2/3, 3/4, some observations on doing research, and from my own experience, which is now a little bit old. All of the results that you're going to see, disclaimer, are old, but hopefully the observations are timeless. We'll see. And then second, some observations on creating Sublime user experiences, which is based on a more recent interest of mine. So for this first talk is going to be on research and wizardry. And the reason I entitled it that is because you'll see that everything you need to know about how to do research is really in the Wizard of Oz. And you'll see that in a moment. So in this part of the talk, I'm going to give you kind of my personal history, which more or less coincides with the history of the field of computer graphics, too. I mean, I felt like the field had already was completely mature when I came to it. But in retrospect, it was still early days, and it was really nice to be able to sort of grow up with it and be a part of it. So for a long time, the history of computer graphics really is the story of a quest for visual realism. And it sort of begins a little before my time with Jim Blinn and Martin Newell, who modeled Martin Newell's wife's teapot, and were able to get beautiful reflections and so on. But I think I do want to point out to you that early work, there were these jaggies. You can see the little staircasing effects along the sides, and I'll mention that again later. This is actually Martin's original teapot, and one of the exciting things about coming to Adobe 10 years ago is that Martin worked at Adobe 10 years ago, and he led the graphics research group, which is essentially the precursor to the lab that I'm running today. Well, Gavin Miller and I both run labs. Those people report to Gavin Miller. So it's not exactly the precursor, but it's a group of people doing similar work to the work that my lab is doing. So this is his actual original teapot, which you can see in the Computer History Museum in Mountain View. Here is an image from Turner Whitted. This is the first ray-traced image. Apparently, people were talking about the possibility of doing ray tracing and getting effects like refractions and reflections and shadows for a long time, but Turner actually went and spent all the CPU cycles and computed this. And this is as close as you can have to an original, because I got this digital image from Turner Whitted. These are the pixels he computed, which is very nice. This is my own little foray into realistic rendering. I was working with Tom Banshoff at Brown as an undergraduate, and this is a rendering of a mathematical surface. It's a Mobius band that has a S-shaped cross-section, and so it wraps around and makes this interesting shape. And we were making movies and so on to understand his mathematical ideas. And when I applied to Lucasfilm, this is the one image I sent along with my CV. And later, I was working there, and Alvy Ray Smith, that following year, I remember, was interviewed by Computer Graphics World. How do you get a job at Lucasfilm? And he said, well, you know, we just hired this guy, this young guy from Brown, and he sent us one picture, but it showed us sort of everything we needed to know. He had nice, smooth, anti-aliased edges. He had some sense of composition. He had this and that. So I'm still proud of that image, and I'm happy to show it to you. So this is the group. This is maybe about a year after I was there. I think there were only about half a dozen of us when I joined. You can see John Lasseter on my right. I'm the guy wearing the shirt that I've got on today. You can see that I still have that shirt. And it still fits. It's amazing. Can't believe it, that it's still there. I thought I forgot to bring it, but then I woke up in the middle of the night, I forgot my shirt, and then I looked in the morning and, oh, I did bring it. Okay, so I'm going crazy. Anyways, So when I came to Lucasfilm, this is one of the first things I got to work on. They were already putting some of the finishing touches on this. This was like the most realistic thing that had been done to date. And it had Alvy's fractal plants, and it had Lauren Carpenter's fractal mountains, and it had this nice pavement texture. And it was called the Road to Point Reyes. Actually, Point Reyes is a place, of course, in California. And it's also was the name of the renderer, which stood for renders everything you ever saw. So this is a little bit of a play on words. And I came and I wanted to contribute somehow. And I said, well, how about I put some ripples in those puddles? And they said, great, do it. And so I figured out how to put some ripples in the puddles. And that was my contribution to this image. Once I was there, we hired John Lasseter after that. And we decided to try to make an animated short. And again, we were trying to push the limits of realism, and we actually took like long hikes together in the woods and sort of pointed out, all the grasses and the rocks and the leaves and what was it going to take, how many polygons would we need, and so on in order to create something really real. There was also a Maxfield Parrish exhibition going on in San Francisco at the museum at the time too, and we all went to that, and we were inspired by the look of his paintings. So this is a little bit realistic in terms of the complexity of the geometry, but also tried to give that Maxfield Parrish look as well. And we showed this at SIGGRAPH in 1984. At the time, it took so much compute power to do this that even though Lauren and Rob Cook had gone to Minneapolis to babysit the Cray computer, computing the frames for weeks, it still wasn't done. So parts of the animation were shown in wireframe, actually. That's how long it took to compute. So soon after that, I decided to, well, actually, I guess I hadn't gone yet. So meanwhile, at Cornell, Michael Cohen and others were working on pushing the limits of realism as well. And rather than just like unlimited geometry in order to get realism, they were looking at how light reflects around a scene and the physics of light transport, essentially. And they were actually doing real experiments where they did a simulated box and they built an actual box, and they took photos of each one and compared the two to see how accurate their simulations were. And actually, I got to meet Michael soon after. He came to Paris, and I remember he showed me these slides of the work that they were doing at Cornell, which was really impressive. And so I decided to go to Cornell and spend a year. It was actually after I took a job at University of Washington. I negotiated with Jean-Luc Baer, who was the chair at the time, and I said, I want a pre-sabbatical for a year. And he said, oh, okay. And so I went and decided to spend a year at Cornell and kind of came up to speed in computer graphics again, because I'd spent a few years doing other things for my PhD. And I worked with Brian Smits and Jim Arvo, and we worked on light transport and global illumination. And we published papers. Here's just an example to show you, yes, there was like real physics and all that stuff in the papers that we published. But when I came to University of Washington the following year, I felt like it's time for me to sort of set out in my own direction and choose some research direction that really I loved. And I could do the physics, I could do the math, but it wasn't really in my heart. And I felt like I should try to figure out what's my special secret superpower, the thing that kind of makes me special, more different from all the other computer graphics researchers out there. And I felt that actually for me, it was thinking about art. I had taken lots of art classes throughout undergraduate, throughout graduate school. I'd spent like the majority of my time at Stanford in the printmaking studio instead of behind the computer. And I thought maybe I can bring some of that to computer graphics. So my first observation for you grad students is that when you're choosing your research area, think about what are your special talents, what's the thing that really drives you and makes you different, and maybe try to choose something that takes advantage of that. Or even if you're not doing that during your PhD, during the next phase of your career might be a good time to think about that. So when I started thinking about it, I realized that, well, actually illustrations have a lot of advantages over photorealism. This might be an interesting area to explore. For instance, they're much better at omitting extraneous detail. So if you look at David Macaulay's book on the way things work, he doesn't show realistic gears. He shows these sort of like watercolor and ink illustrations, and you can put diagrammatic elements like arrows and so on them and understand clearly the mechanism. They're good at focusing attention. So your eye just naturally goes to this upper part of this illustration where more detail has been added. You don't need a big red arrow or big circle to say, look at this part over here. So they're nice for that reason. They're great for clarifying and simplifying shapes. And anytime you have a medical atlas, it's going to show you an illustration along with it so that you can really understand the structure and what's going on. They're good at exposing parts that are hidden. So around this time, I was shopping for a car, and I picked up the brochure and for a Honda, and it shows this shock absorber thing in the chassis, and you can see how it relates to the chassis around it in a really nice, elegant way. You don't have to have a cutaway view necessarily or something to do it. And it's good at showing that ideas are approximate. So for instance, soon after I came to University of Washington, Brian, I think you and I together visited Dale Chuli's studio. Is that right? I think we went and we visited. I remember visiting. It was probably with Brian. We'd been working on doing some realistic glass stuff and refractions and reflections through the glass. And we went to the studio and we said, wouldn't this be great? Can we collaborate? You know, wouldn't you like that when Dale goes to a client and he's trying to sell $1 million chandelier to them, wouldn't he like to be able to show what that chandelier would look like in their environment and all that? And they said, oh, no, that's the last thing we want, because you know, then the clients they're gonna be picky about it. They're gonna say, I want you to move this over there. I want you to, or when it arrives, it's not gonna be exactly the same. They're gonna be upset. You know, when Dale goes, he just draws this big sketchy thing, and then they're like, they say, yeah, we'll buy that. We're really happy with that. And then they're delighted with whatever comes. And so, you know, they get the idea through this sketch that it's definitely an approximation to what they're going to get. And architects do the same thing by conveying that it's approximate. And they're great at adding a sense of vitality. This is Jack Lambert, who taught illustration at Cornell, and I was lucky enough to take some classes with him on actual drawing illustration. So the challenge then becomes, how do we use computer graphics to communicate in the most effective way? And so some of the early work that I did here at University of Washington was with some graduate students here, obviously, George Winkenbach in this case. We looked at pen and ink illustration. That was a good place to start because at the time we couldn't afford color printers. Actually, there weren't any color printers in the department. They were black and white. And there were also some well-established conventions for how pen and ink artists do architectural forms. So we started studying the books and figuring out how we might use sort of black strokes, black on white, to create grayscale and to create also a sense of the texture. And what we realized is you can't just like make it dimmer or brighter the way you do with an image. You have to use more or fewer strokes. And we noticed that what artists would do is if they want a light, say, brick wall, they might just draw the outlines. And if they want it darker, they might fill in some of the bricks. And if they want it darker still, they might start hatching on top. So we had a procedural renderer that would do all these different kinds of textures with black on white strokes. And it would create images like this from a 3D model and a light position and a camera position. And here you can see how some of the things that we programmed into it do show how things will be more clarified in illustrations. For instance, the dividers here, you can see that there's a black edge where the divider is in front of the shade. And that distinguishes it from the shade. And you don't have to play some kinds of tricks to get that to happen. The software would automatically notice these two things are the same color, but they're different objects. Let's draw an edge the way that an illustrator might have done. There's some other subtleties here, but I won't go into them all. Later, the next natural thing seemed like, let's do watercolor so that we can eventually do watercolor and ink illustrations too. And so we read lots of books on what are the effects that watercolor artists care about. We even went to Daniel Smith here in Seattle, which fabricates watercolor inks, like high-end professional watercolors. And we talked to the chemists about how they make the inks and so on. And then we used Navier-Stokes' simulation of shallow water layers. We worked with people in the applied math department and simulated all these same kinds of watercolor effects. One of the effects is this last one on the right, which is the effect of glazing. And that's something that I guess good watercolors do, according to those chemists at Daniel Smith, that bad watercolors don't do. You can put down the watercolor and let it dry, and then you can put down another layer without it picking up the first layer. And so watercolor artists will often use that to get a kind of nice translucency effect. So then we worked on doing automatic watercolor illustration. You can start with an image, and the computer can iteratively apply either water to make it more light or pigment to make it darker. and it will try to achieve various sort of color separations, and those things on top of each other would be separate glazes, and together they form the watercolor image. So here's a video of that as it progresses, creating that watercolor image completely automatically with a computer doing a wet-in-wet simulation, adding water, adding pigment, adding water, adding pigment, until it essentially converges. And this is a low resolution video, but here's the higher resolution result is here. So after a number of years of doing this kind of work, well, maybe what I should say, well, when should I say what? I don't know. After a number of years of doing this work, it started to be a thing. Like there were whole sessions at SIGGRAPH that were on non-photorealistic rendering. There was even a conference that I helped start called NPAR, which was on non-photorealistic animation and rendering. And there were lots of people doing all kinds of effects, pastels and stained glass and all sorts of things. And I think the point here of observation number 2 is that it's useful to think about something different to do. I think in research you find that what happens is that someone does something completely different and new, and there's a lot of low-hanging fruit there because it is different and new, and no one really thought to look there before. So it's easy, and you can get nice results, and you can publish them, and so on. And then gradually, more and more people start working on it, and the fruit's sort of higher and higher and higher, and eventually, 10, 20 years later, there's still people doing it. Now it's gotten really hard because all the easy stuff's been done. And it's not even that exciting anymore, in a way, from a research perspective. And so what I want to encourage all of you to do as grad students is think about leaving the mainstream and doing new things that are different from anything anyone in your field has done before. And you may get some resistance to that. I remember suggesting to my students that we publish X or Y or Z in SIGGRAPH, and they'd say, but SIGGRAPH has never published anything like that before. Why would we be able to publish that there? And I'd say, well, let's try. I mean, where else would you publish it? It seems like the right place to me. And so I think it's a good way to go. Don't get caught in the sort of research eddies. Keep going. Try out new things. So after all these years, as I said, a lot of people are doing this kind of non-photorealistic illustration, and I was thinking, this is really a lot of work, having to study what the artists do and encode them all in rules and write all this hard code to do it. I wonder if we could just reason by analogy. And I had an intern at Microsoft Research at this time, Aaron Hertzman, and I said, let's try thinking about if we could do things by analogy. So for instance, if you had this photorealistic image A, and you have the watercolor illustration A prime that corresponds to it, doesn't matter how it was created, maybe it was created by hand or who knows, and then someone gives you a new image B, is there some way you could synthesize the new B prime just by analogy from the first pair? And it turns out you can do this. You can use a kind of texture synthesis approach to create all those pixels of B prime by sort of pulling in pixels of A prime in places where B relates to A. So you kind of do this pairwise texture synthesis. And the nice thing is now you can take completely different examples. So you can start with A prime being like a stippled image, and A, we just applied some filtering operations to create a grayscale equivalent, and then you give it an actual image B, and now you can automatically, through image analogies, create the stippled version, B prime. And here's another example. This is a rug that I had, and we took a high resolution little part of it, A prime, and I blurred it for A, and then I said, what if you had just the whole blurry rug as the B? Can you kind of hallucinate what the high-res version would look like? And you get some detail that's plausible, actually. Probably the further back you are, the better it looks. But it looks a little bit noisier up in front. Here's an example after we published the paper. We put the code online. We presented it. And I really like this example because we didn't think to do it. It was someone else who took the code and used it for his application. This was a guy who worked at a flight simulator company in Finland. And he had some topo maps, and he had some satellite images. But he also had some topo maps where he didn't have the satellite images. And he was able to use image analogies to create that satellite imagery as well, and then put it in a flight simulator and get the effect of flying over all of that terrain, too. So on to observation number 3, which is about posing research problems. I think that probably most of you, when you came to grad school here, you thought you were going to learn how to solve hard problems, solve hard research problems. And yes, you will, and you do, and I'm going to talk about that too in a little bit. But the thing that I was always looking for in my grad students as they developed and matured in the program was when they could really pose good research problems on their own. I didn't expect them to be able to do that when they came, and usually we'd talk and I'd kind of suggest something and they'd start with that. But by the end, they were the ones who were suggesting the next things to work on. And if they were great ideas, I was like, you're done. Okay, you know how to solve them, and now you know how to pose the problems too. That's great. But it's a difficult thing to learn. That's the thing that I think really, really takes time. And I'd say in a way that's what I'm looking for when I'm hiring people into the research lab at Adobe is who's got really good ideas for what they want to work on, not just how to solve the problem. So let me go back one more slide. I tried to teach and sometimes co-teach seminars in this. It was versions of 558, which were based on a class I had at Stanford with Don Knuth on how to solve research problems. But in my class too, it was also about how to pose research problems as well as how to solve research problems. And every year that I taught it, we would take a different theme. And so I want to tell you about a couple of, maybe 2 or 3 different projects that came out of, I guess 3 projects that came out of one such of those seminars. And so at the beginning, the motivation that I gave to the students was that our sense of aesthetics is derived from our evolution in the natural world. So here's some cute pictures of my kids when they were little, and this is in, I guess this is in Bora Bora, actually. And here's another beautiful nature picture from Costa Rica, and here's one from Guatemala. So these are the sort of things we were evolved to, our visual system was evolved with. But Ellen Dissanayake, who's here at University of Washington, an anthropologist, has written about the human need for aesthetics. And she writes that humans were evolved to require these things. Simply eliminating them creates a serious psychological deprivation. Social systems that disdain or discount beauty, form, mystery, meaning, value, and quality, whether in art or in life, are depriving their members of human requirements as fundamental as those for food, warmth, and shelter. So she's talking about the value of aesthetics in our lives. Well, what's been happening over the years is that more and more of the human population is moving into urban areas. And we, not that long ago, crossed a threshold where now more humans live in cities than in urban environments. And that trend is just continuing to rise. And so here's an example of an urban environment, not a natural environment. Does anyone know what city? Anyone recognize? This is Tokyo. Sorry, did someone just say Tokyo? Tokyo, good. Yes, this is Tokyo. So a lot of what we see are man-made forms here. And in fact, Bill Mitchell, who was the dean of architecture at MIT, told me that he could recognize which software tool was used when he sees a building. He knows what tool was used to design it. And I've heard even that the CTO of Autodesk has said he can tell you which version of which tool was used to design the building. That's how aware he is of it. So the tools that we have really make a difference in the kind of aesthetics that we have around us. And similarly, before the advent of the printing press, all of the commissioned writings had this beautiful kind of ornamentation as part of the page. But once the printing press came along, that pretty much went away, and we just have the words on the page devoid of all of these beautiful aesthetics. So now we've got modern tools, we've got computers. What can we do to kind of add some of that, inject some of that old ornamentation and so on into our tools so we can create them in the objects that we actually experience in our daily lives? So that was the overall theme of the class. How do we use the power of the computer to bring good design, including ornamentation, back into our lives? And the first, okay, I guess before I get to that, I'll give you like rule number 4. Why does it say rule? It should say observation number 4. Anyway, I think I changed the rules to observations and forgot one. But this thing is about solving hard problems. And I would say to solve hard problems with the best tools you have, with strong collaborators, and above all, perseverance. Oh, I haven't really been pointing out how the characters of The Wizard of Oz fit with these rules, but hopefully you've been noticing that yourselves. I think Dorothy beautifully characterizes perseverance and working with strong collaborators. in her case. So problem-solving tools. So that's one of the things we do. So one thing you do if you have a really hard problem that's like too hard to solve is you narrow it down. You reduce the scope of the problem. You take it from 3D to 2D, or you look at simpler cases. So the first problem I said is let's learn how to create ornament. Okay, that's a big, wide open area. How do we even begin there? Well, let's start by classifying ornament and understanding what kinds of ornaments there are. Maybe we'll find some portion of this taxonomy that's worth studying. So one thing you could do is you can classify by the type of area, whether it's ornament that fits into a band or that forms the border that's kind of a very sharp thing on one side but kind of open-ended on the other, or whether it's in a panel, so in a given geometric area of the plane, or whether it's supposed to cover the entire plane. So that's a classification or taxonomy of ornament. And you can also classify by design type, whether it's geometric or whether it's using plants or animals or physiographic things like waves or artificial man-made objects. And so we decided, all right, actually what I did is I asked the students in small groups to pose their problems. That was part of what we were studying. So, figure out what's going to be the interesting thing to work on. So one group, anyway, worked on floral ornament within panels, which I think is a really nice sort of doable size problem. And so the idea is how do we sort of grow plant-like ornaments to fit well-defined geometric shapes? And the way that we did it was with a kind of an L system grammar where you would define the growth rules, and then the ornament would sort of grow to fill the space. And it would do that by iteratively at each step looking for the biggest unfilled area. So that's what those little yellow circles are, is they're looking at, it's testing the circle of biggest radius that doesn't touch anything, and then invoking a growth rule that was suitable to grow into that area. And you could write different growth rules for different kinds of ornaments. So here's 4 different ornaments, each generated by a different rule, filling a certain kind of space. Here are those 4 kinds of ornaments filling a different space, and they just sort of grow organically to fill them. And here's the paper that we ultimately published, where we were able to work around it. Actually, I guess I should give a shout out to Stephen Spencer if he's here, because he was the ACM digital publication chair or whatever at the time, and I think normally there's a copyright on the first page, which we could have grown around, but it wouldn't have been as pretty. So we got him to agree to let us move the copyright notice to the second page, so it would be a prettier ornament around the first page. Okay, a second problem that we looked at in the class was about how did Escher do what he did. So Escher, as a young man, went and visited the Alhambra. I think he was 24, and he took a lot of sketches of the geometric patterns that he saw there, and he was fascinated by them. But he thought it was a pity that people were sort of restricted by religion to using geometric forms, and he wanted to try using animal forms and other things. So in his notebook, he started sketching, all kinds of interesting tilings that he came up with. And so, you can pose the question, can a teapot, the canonical computer graphics object that we saw at the beginning of the talk, can that tile the plane? And of course, I don't know the answer. I didn't know the answer at the time. Nobody knew the answer, but it's a reasonable question. How would you solve it? So this is something that as a class we began to work on. And so here's another problem-solving tool that's very generally applicable, which is take a hard problem and break it into sub-problems, each one of which is hopefully more manageable. And so you can break that problem into, first of all, selecting a good set of tilings. And here, we were lucky enough to have Victor Grumbaum on the faculty, he was an emeritus faculty. I think he's still an emeritus faculty in the math department. And he had written the Bible on tilings and patterns. And so I was able to persuade him to join our class for a few weeks and kind of help us with this part of the problem, which was fantastic. So that's where another example of strong collaborators is really, really helpful thing. So you select a good set of tilings. It turns out that the isohedral tilings, of which there are 93 different types, and he's the one who defined, who sort of realized what all these types were. Turns out that gets you almost all, like 98% of everything Escher did was one of those isohedral tilings. Then you have to find good parameterizations of these tilings. That means ways that they can deform, or all the ways that they can deform while preserving the symmetries of that tiling group. And that's actually a pretty straightforward exercise. No one had really done it before, but it's pretty easy to do it once you understand the symmetries that that tiling encodes. And then you have to define a measure of closeness. So you want something where it doesn't matter what the rotation or the scale of the thing is, as long as the shape is the same, it should give you a close metric. And it turns out that this had been studied in computer vision, and so there was a polygon-to-polygon similarity algorithm that was very simple to use, and we could employ for that. And then finally, you want to use optimization. And so what you want to do is, like, say you want to have a tiling of the thinker, you outline it, that's the target that you're trying to create a tiling from. Now, you're not going to be able to tile that shape exactly. So the easy way to do this is to start with all of the different 93 canonical tilings, and they all start out as simple triangles or squares or hexagons, but then deform each one of them, try to get it toward the thinker, essentially. And so we use simulated annealing to do that on all 93 different types at once, and iterate on them to try to get them closer and closer and closer. And eventually, you can start saying, you know, these ones are getting closer and these other ones don't seem to be working so well. So we'll keep iterating on these with simulated annealing, and eventually you eliminate more and put more of your computation into the ones that are working best. And then finally, you get to just like 2, and then finally the one that worked the best. And from that, you just texture map it with the image, and you create the tiling of the plane. So here's a few examples. Does Tux tile the plane? And the answer is yes. You know, that's a deformed version of Tux, but he tiles the plane. And something that was kind of fun was that Craig was in the last session at SIGGRAPH. Craig Kaplan, who was the co-author on this paper and a student in that class and graduate of University of Washington, of course. He was in the last session, so he was able to take all these images that people had used earlier in the conference and show Escherizations of those images, which was very fun. Can the teapot tile the plane? Yes, there's the teapot tiling the plane, or a close approximation of it. So what about Escher? Well, yeah, Escher. Escher's self-portrait tiles the plane too, as it turns out. So going back now to his earlier work at the Alhambra, another project that we began looking at in this same seminar was how to create Islamic star patterns. And you know, these can be found all over the Islamic world. They're just gorgeous. But nobody really knows how they were designed. It was a secret that was passed from master to apprentice and eventually died out. So the idea was, well, can we build a design system using sort of modern ideas, modern mathematical ideas of tilings and patterns and so on, so that we can create a design system where someone could come up with their own patterns along these lines. And it turns out that you can. It turns out that if you start out with a set of tilings called the Archimedean tilings, and you basically run a kind of algorithm that builds a scaffolding over them, and there's some parameters there that you can adjust, and however you adjust them, it kind of looks nice. You can build these kinds of Islamic star patterns. And so here's a couple of examples of them. Now, this is work that was very frustrating because we submitted it to SIGGRAPH one year and it was rejected. And so we said, okay, that's a great opportunity to, like, you know, add even more stuff and do it even better, and we'll resubmit the next year. And we did it the next year and it was rejected, and then, you know, it's not always easy. But the nice thing is that that did push us further and further and further, and we ended up kind of building these Islamic star patterns in something called absolute geometry, which is non-Euclidean geometry, basically, which sort of ignores the Euclid's fourth postulate about that for every line and point, there's one line that's parallel to it. And if you don't assume that, you get something called absolute geometry, where it encompasses things on the sphere or the hyperbolic plane as well. And so these same designs, because we wrote it in such a way, there we go, also work on the sphere, and they also work on the hyperbolic plane. That's a Poincaré projection of the hyperbolic plane. Here's another example of the same pattern over the sphere and over the hyperbolic plane. So we eventually did get it published in TOG, in Transactions on Graphics, where by that time it had become a big, long paper with lots of mathematics, and so it was a more appropriate venue for it anyway. So a nice thing is that this came full circle into the real world. Nathan Myhrvold, who probably a lot of you know or know of, he had been the CTO of Microsoft. I think he started Microsoft Research, and he was retired or semi-retired, or hadn't yet started intellectual ventures, and he was building a big, beautiful house somewhere. I haven't been to it, but maybe some of you have. I don't know. And he had bought a water jet cutter. These are like things that these are water jets that will cut through metal, and they'll cut through wood, and they'll cut through anything. And you can cut elaborate patterns. And he wanted to design his own like heating grates and window shades and things like that. And so he used this tool, Taprats, that Craig built in order to create all of his own Islamic star patterns and actually fabricate them and use them in his house. I saw him not that long ago and said, I'd really like to get a picture of the things in your house. And he said, yeah, I'll send you one. And I never got them. So the last thing I want to mention about this part of the talk is the final observation is to embrace hard problems. It's like we all want to avoid hard problems in our life, right? But when you do a PhD, you can't get a PhD without finding a hard problem and solving it. Like if you just work on easy problems, you're not going to get the PhD. And I think it's a lesson for life as well, that hard problems are going to find us anyway. Rather than running away from them or trying to avoid them, it's better to really embrace them and take them head on and figure out how you're going to solve them and surmount them in a sense. Okay, so now we get to part 2. So I mentioned that this relates to the first part in one sense, which is I said you should follow your heart. Figure out where your heart is going, do that. Well, my heart has followed tango for the last 7 years, actually. Is Zoran here? I don't know if Zoran's here, but he was always dancing tango when I was here in the department, and I would go to parties at his house and meet other tango dancers. I was always curious about it. And finally, I guess about 7 years ago, I started it, and I've completely fallen in love with it. And I think there may be some lessons from tango that could help us design better user experiences. So this is a kind of a HCI part of the talk. But first, I want to show you this New Yorker cartoon that seems relevant somehow. This guy says, I swear if someone told me 10 years ago I'd be sitting naked on a tree limb talking to a can of peaches and syrup, I'd have said they were crazy. And I sort of feel that way about, if someone told me 10 years ago I'd be up here at a Distinguished Lecture Series talk at UW, CSE, talking about tango, I would have said they were crazy. But anyway, here goes. So when you think of tango, probably you think of this, which is kind of the elaborate show tango that you see if you go to a show in Buenos Aires. Often the dancers are lifted off the floor and, all these dips and all these crazy things. But the experience of dancing tango is much more like this. It's much more of an inwardly focused, concentrated activity. I came to discover that it's not about showing off. It's not about the effect that it appears to have to other people that might be watching. It's actually nothing to do with that at all. It's all about the internal sensations that you create between you and your partner, and your eyes can be closed. Well, for the leader, generally your eyes cannot be closed because you may hit other people or a wall or go off the dock or whatever. But if you had unlimited floor space, then your eyes could be closed too as a leader because it's all about the inner sensations that you're creating. And when thinking about it, it makes me realize that the mental state that you're creating with tango is one of flow. This is this mental state that people talk about a lot these days. It was invented by, or discovered in some sense, by a guy named Mihi Csikszentmihalyi. Can't say his name that well, but he's been studying this and writing about it and lecturing about it for years. And it's this mental state of being fully immersed in an activity, accompanied by feelings of energized focus, full involvement, and enjoyment in the process of the activity. So it's a single-minded immersion. It's like being in the zone. We all have experienced this at some time or another. It's when time just flies and you don't realize an hour went by or a whole day went by or whatever it is because you were so engrossed with the activity. And it's considered a very pleasurable sensation. Everybody wants to have it. And it's also been shown that it's associated with optimal performance in sports or in like musical performances, with artistic and scientific creativity, with further development of skills, with a sense of high motivation and intense feelings of enjoyment. And in fact, Adobe, I just noticed like yesterday morning, even seems to be using this new tagline. With Creative Cloud, your creativity just flows and your potential is unleashed. So I mean, it's in the vernacular for sure, this idea of flow. But one cannot force a state of flow or even predict when it's going to happen. It's almost like, you know, trying to force yourself to go to sleep or trying to force yourself to fall in love or something like that. You just can't make it happen. But the question is, can a state of flow be fostered? And that's where I think Tango comes in. I think that what I've been learning as a leader in Tango is how to create a state of flow for the follower. The question is, you know, can our software do this same kind of thing? And I'll say it's not just a weird analogy or metaphor, because the follower, well, that's a human being, that's a person. The user, that's also a human being, that's also a person. So the same kinds of things that work in one thing could very well work in the other domain as well. Oh, I forgot. I was going to play you just a little bit of Tango, just so you can have a sense of what that's like. One more second. There we go. Could be louder. Should be louder. I guess we'll stop about there. Just wanted to give you a sense of some Tango music. Hard to choose a single one because there's so much beautiful music there. Anyway, so what lessons can be applied? Let's go through. So first lesson, never present a jarring moment. So when I was studying Tango, or beginning to study Tango, I was hoping that with every lesson I was going to learn something new, some new cool move that I could do, because out on the dance floor you see all this really cool stuff that people do, and I wanted to do that too. I really wanted to do that cool move and that cool move and that cool move. What did they just do? And what my teacher began to finally get me to realize is that it's not about learning to do more and more fancy moves. What's really important is to learn to not have any bad moments for the follower, to not create any kind of thing that's going to take her out of this trance. So you can do this really simple stuff. If you're doing it well, she'll be in this beautiful trance and she'll be pleased. But if you try to do something complicated and you don't do it well, and she comes out of it, and that happens more than once or twice, like, forget it. She's just never going to dance with you again. It's over. Well, in software, I think the same thing is true. I mean, we think about, in my lab, we think about, you know, what are all the cool, new, exciting features that we can add into the software? But really, more important than that, if you want to put people in the zone, is to think about what's the worst moment that the software gives to the user, and let's improve that. Let's raise the lower bound instead of raise the upper bound of the experience of this software. And for each one, I'm just going to give an example a little bit. I was trying to think of examples. I'm really impressed with the After Effects team at Adobe. One thing they do is they take their new releases and they go to their users and they don't tell them anything. They just say, go ahead, use it. You know, let's see what you do. And they watch. And anytime the user, you know, gets confused or doesn't know or whatever, they write that down. Okay, you know, that's good to know. Or keep going, you know, or they might help them through that, but they keep watching and observing, and then they go back and they fix all of those jarring moments, or they try to, or at least the worst ones. So I think they do a really nice job of trying, at least, to address this. A second lesson, adapt to the user's level. I'm going to read you a little bit of a blog post from a woman. Her name is Sally. She went she's British, and she went and lived in Argentina for a while just because she's so immersed in Tango, and she writes a blog about it. And so here's from a blog post, and it's a little long, but I've definitely tried to edit it down. She talks about this, the slow reveal. The first time I dance with someone new, this is what seals the deal for me. In short, he knows how to listen to me. He starts simple, and he finds out what I can do. He listens to my body, my degree of relaxation, my level of confidence, my ability, and then he makes me feel like a goddess. As he works out who I am and feels me relax in his arms, He gradually reveals his dance, his ability, his character, his little musical tricks and treats, depending on the music, his mood and mine, and how I respond to every tiny thing he does. He knows there will never be a moment when I don't understand what he asks of me because he only ever dances what he knows I can handle, and if he is really clever, what he knows I desire. He never allows me to feel that I made a mistake. He is far too wise. So in tango, it's really the leader's responsibility to make the follower look and feel like a gifted dancer. And it's an interesting challenge that you can actually do. You can take someone who's a complete beginner, and hopefully, if you're good enough as a leader, and also the reverse is true, but even more difficult, if you're good enough as a follower, making the leaders change. If you're good enough, you can actually have a really wonderful experience, and the woman can look like a gifted dancer as well, even if she's a total beginner. And I've had that experience early on, going to Buenos Aires and dancing with someone and thinking, oh, that was just awful. And then seeing her dancing with a more experienced leader and going, wow, she looks great. And realizing that, it's my inadequacy, really, that I wasn't able to adapt and adjust to her level the way I should have. So in software, rather than presenting a uniform interface to all users, how can we adapt that interface so that the user will always feel proficient and in control? And I was trying to think of an example. I realized probably the best example is computer games of all kinds, where there are levels essentially, and you don't start a computer game at level 10 where you're just going to get blown out of the water or whatever. They start you easy, and it sort of is adapted to your level. And as you graduate, you go to the next level, and it's more challenging. As you graduate, you go to the next level. So how can we bring that kind of a sense of design into other software where it will, again, adapt to your level and hopefully do it automatically, like be able to identify what your level is and give you an appropriate interface at that time. Lesson number 3, respond without fail in real time. So when you're dancing tango, there's so much going on at once. There's the music, there's the dance floor, which might be crowded and constantly shifting, where there's space, where there's not space, the way your partner is responding. And everything you do has to be managed instantaneously and gracefully. You don't get a second chance. You can't go back and rehearse or do it again. You can't apologize. It's a performance. It has to be just perfect as it can be all the time. And so in software, I think we can think about the same things. How can we architect our software to integrate multiple complex operations? Say you're fetching data from the cloud and you're splitting your computation between the client and the server and all these things going on without ever breaking at least this illusion that there's a fully real-time response at every given moment. And it may be an illusion, but still, how do you create that illusion at least to keep someone in the zone? So one example, this is something that we're working on called Portrait Studio. It's an app that we're designing in my group. It's just an experimental thing. But the idea is if you take a photo of yourself, it will start applying professional photographer looks to your portrait. And some of these things are really simple, so it's going to give you a whole variety of different looks. And some of them are easy to compute and can be done right there on the phone where you took the photo and delivered instantaneously. Other things require a lot of data and training, and you have to send the image up to the cloud, and it has to do the computation there, where it can use all that data and then send it back. So the idea, which, like I said, it's still under construction, is that it'll artificially slow down the presentation of the results that were done on the phone. So you see one, and then another, and then another, and then another, and then by the time you've seen all those, now things are starting to come in from the cloud, and you see those coming in as well, but you never get this sense of I'm waiting because there's just this damn spinning wheel or whatever while I'm waiting for something to come in from the cloud. So I think those kinds of things, in order to mask any waiting and give you something to focus on as a user, is nice. Level 4, create a highly tuned dialogue. So this is, I took a workshop in Seattle early on from a guy named James Friedgen. I think he's moved to, I know he moved to Sweden, and now I think he's in LA or something. But he used to have a school here called the 8-Style School of Tango. And I remember he kept repeating in this sort of Zen-like way, without ever explaining it. He kept repeating, the leader is clearly in control. The follower is actually in control. And he would say this over and over again, and nobody knew what he was talking about. And I'm still not really sure, but I think I can. At least this makes me think of something, which is interesting to tell you about tango, which is that in tango there's a dialogue that's very highly precise and tuned between the leader and the follower. So it's not like the leader just takes a step and expects the follower to like stay with him. No, I mean, if you did that, they'd be falling all over the place. It's impossible to, in real time respond to someone else's movement. So what you actually do as a leader is you kind of use a slight pressure change to indicate to the follower that she should take a step, and then you follow with your step. So really the leader is following the follower. And in that sense, she's sort of actually in control. She doesn't have to move. She is not going to move until she wants to move. But when she finally wants to move, if you're a good follower, a good leader, you will then follow her. So in software, how can we create software that participates in a similar dialogue? So all along, and I'm keeping this sort of thing, the leader is like the software, the follower is like the user. So the software would offer options that are apropos at a given time, and then allow the user to actually take control and say, okay, this is what I want. And then the system would then follow through and execute it and deliver whatever the result is, and then offer again, maybe something else that might be apropos. So again, these are hard to come up with examples of where this actually might happen in software. But one example, I think, is Google Search, where you start typing, and it gives you a whole bunch of choices. And usually, one of those is actually the thing you wanted pretty soon. You may only type a word or two, and it's already got the whole long 5-word query that you were asking for. And that's like offering, oh, did you want this? And you select it, and then it follows through with, like, here's the page, or here's the set of pages. Now, one thing it doesn't do, but maybe it should do, is say, and I bet your next query is going to be this. This is maybe or one of these 5 things might be the next thing you want to ask about. Anyway, how can we think about doing more and more of that in our software? There's 8 of these, so I'm almost through. Lesson 5, model the user's state of mind. So in Tango, the only way that you can create a perfect experience for the follower is to have empathy, to really be inside her mind in a way and experience it from her point of view and understand exactly what it is that she's experiencing. Part of the reason I really enjoy following, well, part of it is just intrinsic enjoyment, but part of it is it really helps me understand leading better, to have done a lot of following too, because I can really be in her mind and understand what it feels like from the other side. And interestingly, I think in Tango, when there's really a good connection, she also knows what it feels like for you in your mind, you the leader. And that also kind of involves like an infinite recursion of knowing that she knows that you know what it feels like for her, and that she knows what what it feels like for her, what it feels like for you, and so on. So there's this like double infinite recursion, which only computer scientists would understand. So in software, how do we create software that models the user's state of mind at all times, including the user's own model of what it is that the software might be doing, right? So, because the user's got an idea, and if the software has some idea of what the user might be thinking that software is doing, the software can probably do a better job still. And so, I don't know, here's a possible example. Maybe it's a very early days example of that, but the Nest learning thermostat is supposed to learn your habits and learn what you want, and after some experience of you and your family in the house, it knows the patterns of your life together and can anticipate them. I think probably a better example is still like science fiction, like the movie Her or something, where you have a really empathetic OS that you talk to and that really, really understands you and understands your state of mind. But that's still a few years out. But it's a direction to move toward. Lesson 6, crafting interactions and natural phrases. So in Tango, and this is something that Zoran, I remember explaining to me once, he said, David, it's, because I was saying, boy, Tango is so hard. And he said, it's not really hard. When you think about it, everything's built from 2 simple units. There's basically a step and a pivot, and it's just all boils down to that. Those are like the quarks of Tango. And so that may be true, but to become a really good dancer, obviously you need to get beyond the low-level mechanics of being able to execute a step and a pivot and put things together into nice musical phrases that have dynamics and musicality and so on. And so in software, first of all, how can we craft interactions in terms of a few simple primitives that will compose in powerful ways? Because if you can do that, it will be much easier to learn. And second of all, how can we add a sense of rhythm and dynamics and perhaps even occasional flourishes to the experience so that it's not just kind of a lowest level, I'm going to do this, it's going to do that, I'm going to do this, it's going to do that, but really there's a sense of phrasing to the experience. And possibly an example of this is a new interface for Photoshop that Adobe has recently put out there in preview form called Design Shop. And it's kind of rethought the whole interface for Photoshop and tried to make it much more predictable and regular. And there's like this nice sort of editing cycle where you observe what it is and you pick a tool and you edit it and you can evaluate how well it worked and go on. And the tools all work in consistent ways and stuff. So it's meant to be more of this kind of thing. Check it out. OK. And then lesson number 7 is exhibit subtlety and refinement. So in Tango, it's really the subtlest details that make all the difference. It's exactly where you stand on your foot. And by that, I don't mean like, do you stand on the ball of your foot or the heel of the foot? I mean, do you stand on the front of the ball of your foot or the back of the ball of your foot or the middle of the ball of your foot? And a lot of leads are just that subtle difference from the back to the front of the ball of the foot, not even a whole foot. Or how much tension is in your arms, or just the slightest opening of the chest, a few millimeters, a degree, makes the hugest difference. And that's what takes so long to learn, is all of that subtlety. So in software, too, I'd say the subtlest details make all the difference. And I think the iPhone is a great example of that, where if you look at the interactions, when you swipe from the home screen with the photo on it to the next screen, it does all kinds of subtle little things. The image gets a little smaller as it fades out, and things move at different rates. There's ease in, there's ease out, all different parts. And it's all been very, very finely thought out. Or you get to the end of a list and it kind of bounces a little bit and gives you a sense of physical reality. Those kinds of subtle details make all the difference. And then the last example or the last lesson is integrating learning with doing. So there's a catch-22 in Tango. You can only learn it by doing it, but of course, you can't do it if you haven't learned it. And so it's very difficult at first, and it's always very difficult. So it becomes an iterative process where you learn it while you do it, and gradually you sort of get to dance with better and better people and learn more and more subtle things as you go. And so in software, how can we make learning a part of the immersive experience that we offer? So you don't go to a separate tutorial in a video on Google to learn how to use your Photoshop software. Instead, it could be integrated right in with the experience of using it. And there is an example of this. It was published originally as Tutorial Player. This is work that Mira Doncheva and Will Lee, who are in my lab, who are graduates of this department, did. And it has recently shipped as part of the Creative Cloud Tutorials, which lets you sort of step through operations in Photoshop and actually try them out as you go and learn them as you go. So, final thought. In Tango, everyone, as I said, wants to dance, or maybe I didn't say, they want to dance with only the very best dancers. It's kind of a meritocracy. And similarly, imagine if we had software that would never present a jarring moment, would always adapt to the user's level of expertise, would respond without fail in real time, would create a highly tuned dialogue, model the user's state of mind, craft interactions in natural phrases, and exhibit subtlety and refinement, and also integrate learning with doing. I think that would create a sublime experience and very loyal users for that kind of software. So that is the end of my talk. Thank you.